Today, we're plunging into something absolutely foundational, really, for anyone building software that needs to be reliable. How programming languages deal with things going wrong. Not the everything's perfect scenario, but those moments when a file isn't where you expect it, or the network drops.
Or the input data is just completely off.
Exactly. How do programs navigate that kind of minefield without just, well, crashing?
It really is the difference, isn't it? Between software you can actually trust and software that just feels like it's constantly on the verge of collapse. Every solid application needs a strategy for that unhappy path.
So our mission here is to distill the core ideas. We want to get a handle on the two big philosophical approaches, exceptions versus error values.
The main camps.
See how languages like Java, C++, and Go actually put them into practice, understand the best ways to use them, and importantly, the traps to avoid.
The pitfalls.
And crucially, look at the real-world consequences, performance especially.
Think of it like getting a backstage pass, maybe. Just see how languages handle failure and what that actually means for building software that, stands up when the unexpected happens.
Okay, so where do we even start? The terms themselves can be a bit fuzzy sometimes. Like, what's the actual difference between an error and an exception?
Yeah, that's a perfect starting point, because people do use them loosely sometimes. But the sources, especially the ones looking at Java's design, they make a pretty clear distinction. It's often rooted in Java's throwable hierarchy. Generally, errors, capital E error, in Javaland are seen as really serious problems, often outside the program's direct control and typically unrecoverable from within the application itself.
Okay, right, like running out of memory or hitting a Stack Overflow, things you can't really just patch up in your code logic?
Precisely. Think out-of-memory error or Stack Overflow. These often point to fundamental issues with the system or the runtime environment. Exceptions, on the other hand, well, they're also unexpected events during execution. But they're usually caused by something the program did or encountered. And importantly, you might actually be able to recover from them, or at least handle them gracefully.
Okay, so like file not found exception. You tried to open a file, it wasn't there, but maybe you can prompt the user or try a different path or something.
Exactly. That baking analogy one source used was pretty good, actually. Running out of eggs is an exception. You can probably handle it, right? Maybe borrow some. But the oven exploding, that's an error. Game over, probably unrecoverable from within that recipe.
Got it. Okay. So with that distinction in mind, the sources show that for these recoverable, unexpected situations, the exceptions languages tend to fall into one of two sort of major philosophical camps.
Right, the two big ones. The exception model and the error value model.
Okay, let's dive into the exception model first. That's what we see in languages like C++ and Java, right? How does that fundamentally change how you write code that might fail?
Well, this model is all about interrupting the normal flow of control. When something goes wrong, instead of just continuing line by line, the code signals the problem by throwing an exception.
Okay.
And that throw immediately stops the current execution path, and it jumps, kind of non-locally, up the call stack, searching for a designated place to catch and handle that specific kind of problem.
So you mark the code that might fail with try, you signal the failure itself with throw, and then you handle it somewhere up the chain with catch.
That's the core mechanic, yeah.
Yeah.
You wrap the risky operation, maybe opening a file or making a network call, inside a try block. If a throw happens inside that block or in a function called from within it,
Right.
the runtime starts walking back up the sequence of function calls that got it there. It's looking for a catch block that says, hey, I know how to handle this type of exception.
Okay, and I saw a lot about stack unwinding in the sources, particularly concerning C++ dust.
Yeah.
What exactly is happening there during this jump?
Ah, yes. Stack unwinding. This is absolutely crucial, especially for C++ love. As the runtime searches up the stack for that catch handler, it performs this unwinding. What that means in practice is, for every function call frame, it exits on its way up. It calls the destructors of any objects that were created within that function's scope, and are now going out of scope because we're leaving that function abruptly.
Wait, hang on. Why is calling destructors so important during an exception? Isn't the program already in a failure state?
It is, but that's why it's so important. Because in languages like C++A, destructors are the primary mechanism for releasing critical resources. Things like closing files, freeing memory allocated on the heap, unlocking mutexes.
Ah, okay. Cleanup.
Exactly. This ties directly into the RAII idiom resource acquisition is initialization. The whole idea is that resource management is tied to the lifetime of objects. If stack unwinding didn't happen correctly during an exception, you'd have a nightmare scenario. Functions would exit abruptly, leaving files open, memory leaked, locks held. RAI and exceptions are really designed to work hand in hand to prevent these leaks, even when things go wrong unexpectedly.
So RAII, supported by stack unwinding, gives you a strong safety net even when things go spectacularly wrong. Okay, what happens then if the exception travels all the way back, maybe to main, and finds no catch handler anywhere?
Then typically the program terminates. In C++A, the default behavior is often to call std.terminate. It's kind of the final safety net saying, look, nobody knew how to deal with this specific problem. We have to give up now.
Makes sense. And both Java and C++ have these structured hierarchies for exceptions, right? It's not just one generic something went wrong signal.
Yes, definitely. C++ uses std.exception as a base class, and the advice you see, like in modern C++A, is strongly towards using specific derived exception types. Don't just throw a generic std.runtime for everything. Throwing something specific like std.outofrange gives the handler precise information.
And Java.
Java's hierarchy is even more formalized, descending from throwable. It clearly splits error from exception. And then it further subdivides exception into checked and unchecked types, which is a really big deal in Java because it influences how you must handle them, or rather, how the compiler forces you to think about handling them.
Ah, right. The famous catch or specify rule in Java. I remember that.
Exactly. For checked exceptions, those are the ones representing anticipated external failures like IO exception, file not found exception. They're subclasses of exception, but crucially not runtime exception.
Okay.
For those, Java forces you, at compile time, to either wrap the call that might throw it in a try-catch block or explicitly declare in your method signature that your method throws that exception, passing the buck up the chain.
So you can't ignore them.
You cannot ignore them at compile time. Unchecked exceptions, on the other hand, those are runtime exception, and its subclasses, like the classic null pointer exception or array index out of bounds exception. They're generally seen as programming bugs, things that ideally shouldn't happen if the code logic is correct. So you don't have to declare them or catch them, though you still can if you want to.
Okay, so that's the exception model in a nutshell. Throw, non-local jump, structured handlers, crucial stack unwinding for cleanup, especially with RAII, and in Java, that compile time checking for certain types.
Yep, that covers the core ideas.
Now let's pivot. Let's talk about the other major approach, the error value model. We see this very strongly in Go, and maybe hints of it in types like result or std.expected in Rust and modern C++ Wart. How does this work?
This model takes a fundamentally different philosophical stance. Instead of interrupting the control flow with a jump, it treats potential errors as just regular data that functions return alongside their normal result. The control flow remains completely explicit and sequential, no hidden jumps.
Okay, how does that look in practice? Specifically in Go, since that's a prime example.
The core Go idiom, you see it absolutely everywhere in Go code, is that functions that might fail return two values. They return the actual result they computed, if successful, and also an error value. This error value often uses the built-in error interface.
Two return values, okay.
Right. And the convention is simple. If everything went well, that error value is nil. If something went wrong, the error value is not nil, and it usually contains some information about what failed.
And the developer, the person calling the function, has to check that error value. Is that enforced?
It's not strictly enforced by the compiler in the same way Java checks checked exceptions, but it's a very, very strong convention. You see, if error blocks basically after every single function call that could possibly fail, it's just how Go is written. There's no hidden jump. The program flow continues step by step, and the programmer is explicitly reminded right there in the code, hey, this could have failed. Check the error before you proceed.
Right. So you have this really interesting tension. The exception model can make the happy path, the code where everything works, look cleaner, maybe, because the error handling is sort of off to the side in catch blocks. But the error path itself is implicit, a non-local jump. Whereas the error value model makes both the happy path and the potential error path completely explicit at every step. Why did languages make such different choices?
It really boils down to the fundamental design philosophies and the priorities of each language, just as the sources articulate. C++O, for example, was designed for systems programming. Manual resource management and performance were paramount, so pairing exceptions with RAII offered a way to get safety guarantees automatic cleanup even during complex operations that might fail partway through. That Automator example mentioned in some older C++ material, even though Automator itself had issues.
Yeah, quirky assignment.
Quirky assignment, exactly.
No.
But it illustrates how tying resource ownership to object lifetime via destructors was a core concern from early on, and that model integrates naturally with exception unwinding.
Okay, and Java's focus. More on enterprise applications robustness.
Right, and that led directly to that strong emphasis on checked exceptions. The Java designers explicitly wanted to force developers to acknowledge, at compile time, those potential failures that often stem from the environment, network problems, file system issues. Make those potential failure points highly visible in the method signatures. Force people to think about them.
And Go just went, nope, different direction.
Pretty much. Go prioritized simplicity, clarity of control flow, readability, and efficiency, especially for things like concurrent network services. The Go team, as one blog post detailed, explicitly considered and decided against adding exceptions. After a lot of internal debate, lots of proposals apparently. They stuck with the explicit if equals nil pattern. They felt that, yes, it's verbose, but it makes the error path completely unambiguous and predictable. And they valued that clarity, especially for concurrency and just understanding the code, more highly than the potential conciseness of exceptions. They basically decided that adding syntactic sugar for error handling wasn't worth the complexity and the risk of hiding important failure logic.
It's fascinating, isn't it, that the verbosity is almost seen as a feature, not a bug in Go's philosophy. It forces you to see the error handling path right there.
It absolutely does. And the sources, taken together, they really reinforce that there's no single right answer here. It's always a trade-off. Exceptions can simplify the code's main logic path, the happy path. But the failure path becomes this separate, non-local flow you have to track.
Yeah.
Error values make the failure path part of the normal sequential flow, which can add boilerplate, definitely. But it keeps everything completely visible and explicit.
Okay. Speaking of visibility and making things clear, let's shift gears a bit and look at best practices. Synthesizing the advice from all these different sources, C++, Java, Go implicitly, what are the key takeaways for writing good error handling code, regardless of the specific mechanism?
Well, a really major piece of advice, especially in languages that do have exceptions like C++ and Java, is to use them judiciously. Use them only for truly exceptional situations, things that are genuinely unexpected in the normal flow of the program.
Right, not for normal control flow.
Exactly. Don't use exceptions for things like, say, validating user input, where an invalid entry is a perfectly expected possibility. That's often better handled just by returning a status code, or a Boolean, or maybe an optional or something similar. Exceptions should be for failures that disrupt the expected operation. Some sources also suggest assert is often a better tool for catching programming bugs or precondition violations during development. Things that really should stop the program cold if they happen, not things you expect to catch and recover from gracefully in production.
So reserve exceptions for the truly unexpected failures. Not every little validation hiccup needs to throw.
Precisely. And then when you do handle exceptions, do it thoughtfully. The advice is generally to catch at the right level of abstraction. Not so high up the stack that you've lost all context about what actually went wrong, but not so low level and scattered that your error handling logic becomes duplicated everywhere. Find the place where you have enough information to actually do something meaningful about the error.
Like logging it properly or informing the user.
Exactly. Log errors consistently. Provide helpful feedback if you're interacting with a user, not just a raw stack trace, hopefully. And handle it.
The C++ sources specifically mentioned catching my reference. Why is that important?
Yes, that's standard C++ practice. Catch by const std.exceptionEnd or a reference to a more specific derived type, like const std.runtimeErrorEnd. The key reason is to avoid slicing. If you catch by value and the actual exception thrown was an object of a class derived from the one you're catching, catching by value will slice off the derived part, leaving you with only the base class object. You lose the specific type information.
Ah, okay, so reference preserves the actual type.
Right. And related to that, using specific exception types is crucial. Throwing and catching std.invalid argument when an argument is bad, or std.filesystem.fileSystemError for file issues, allows for much cleaner, more targeted handling than just having a giant catch or catch std.exceptionEnd block trying to figure out what went wrong.
Makes sense. And resource cleanup came up again and again as absolutely critical.
Absolutely central. Beyond RAII being the cornerstone in C++, Java made a huge improvement here with try with resources, introduced back in Java 7.
Right, I remember that being a big deal.
It was. For any object that implements the auto-closable interface, which includes most things that need explicit closing, like file streams, network sockets, database connections, you can declare and initialize it within the parentheses of the try statement itself.
Okay.
And the Java runtime guarantees that the close method of that object will be called when the try block exits. Doesn't matter if it exits normally or because an exception was thrown inside it, the cleanup happens automatically.
That sounds much safer and cleaner than manually putting close calls in a finally block, which was the old way, right?
But much cleaner. It significantly reduces the need for those often complex and error-prone finally blocks whose only job was resource cleanup.
Okay, so clean up your resources. What's the universal sin of error handling, the thing the source is really warned against?
Oh, that's easy. Swallowing exceptions. Just catching an exception and then doing nothing with it. An empty catch block. Or maybe one that just logs a trivial message and carries on.
Why is that so bad?
Because it just hides the problem. It makes debugging an absolute nightmare later on. The program might appear to be working correctly, but underneath, it's encountering failures, maybe corrupting data, or getting into an inconsistent state. If you catch an exception, you need to actually handle it appropriately. If you can't fully handle it at the current level, at the very least, log it thoroughly and then maybe rethrow it. Java's chained exceptions are good here. You can wrap the original exception inside a new, more specific one, adding context without losing the original cause.
Don't just pretend it didn't happen. Got it. Any other specific C++ quirks or best practices mentioned?
Well, throwing from constructors can be a bit tricky. If a constructor throws an exception before the object is fully constructed, its destructor won't run. This can lead to resource leaks if the constructor was acquiring resources manually before it threw, although RAII helps mitigate this for member variables that were fully constructed before the failure. It's something to be aware of.
Okay.
Also, the noExcept keyword, added in C++11, is important. It allows you to declare that a function promises it will never throw an exception. This can allow the compiler to perform certain optimizations. But if a function marked noExcept does end up throwing somehow, the program immediately calls std.terminate. So it's a promise you have to keep.
A high-stakes promise.
Indeed. And then there's the infamous C++ destructor problem that often comes up in these discussions, like on Reddit.
Right. You mentioned RAII relies on destructors running during unwinding. What's the problem?
The problem is the specific C++ rule. If an exception is thrown from a destructor at a time when another exception is already active and propagating up the stack, typically meaning during stack unwinding itself, the program immediately calls std.terminate. Basically gives up.
Whoa. So if you're unwinding from error A and a disruptor called during that unwind tries to clean up but hits error B, boom, instant crash.
Pretty much. And this leads to quite a bit of debate. Some argue that a destructor failing usually indicates a fundamental bug or an unrecoverable situation anyway, so termination is the only safe response. Others argue that resource cleanup can legitimately fail. Sometimes think about trying to flush a file buffer to a disk that's suddenly full, or closing a network connection that's already broken. They argue the language needs better ways to handle these multiple, potentially simultaneous failures during unwinding, perhaps with something like aggregate exceptions, which C++ doesn't really have built-in support for. It highlights a genuine tension in the language design around failure complexity.
Wow, yeah. A tricky edge case. Okay, so the best practices really boil down to being intentional, being specific in your handling, and making absolutely sure cleanup happens reliably using tools like RAII or try with resources.
That's a good summary.
Now let's get to the really juicy part for many people, the cold, hard numbers, the performance angle. Because this is where the exception model and the error value model seem to really diverge, isn't it? This is where that nutrient analysis comes into play.
This is where it gets really interesting and potentially quite eye-opening for people who haven't benchmarked it themselves.
Right.
C++ exceptions are often described with that phrase, zero cost. But that's a very specific claim. It means zero cost if you don't throw. The moment an exception is actually thrown and then caught, there can be significant overhead involved.
Okay, what contributes to that cost? It's not just the jump itself.
Yeah, it's more than just the jump. The sources detail several factors. First, there's the stack unwinding process itself, potentially calling many destructors on the way up. That takes time.
Right.
Then there are lookup costs. The runtime needs to figure out which catch block matches the type of the exception that was thrown. This often involves using what are called side tables, generated by the compiler. and potentially relying on RTTI runtime type identification, which is essentially dynamic type checking. That's not free.
Okay, lookup tables, type checking.
Plus, there's usually the cost of allocating the exception object itself. Depending on the implementation, this might even involve dynamic memory allocation on the heap, which is notoriously slow compared to stack allocation. And finally, all the metadata needed to support exceptions. Those side tables, type information can add to the overall code size, which can have secondary performance effects like worse cache locality.
So multiple sources of overhead. And the benchmarks. What did the nutrient analysis actually show in terms of numbers?
The results from Nutrient were pretty stark, yeah. Their tests, focusing on C++ free, showed that just the act of throwing and catching an exception, even in relatively simple loops with shallow call stacks, could make the code orders of magnitude slower compared to simply returning an error code or using a value-based error handling approach like std.expected.
Wait, orders of magnitude? Like 10x, 100x slower, not just a few percent.
Yes, exactly. We're talking potentially 100x or even more in some scenarios, depending on the compiler, optimizations, and the specific code. And that performance penalty can get worse as the call stack gets deeper, because unwinding has more work to do.
Wow. Okay, that's not a small difference you can just brush aside, especially in performance-sensitive code.
It's really fundamental. It's why you'll often see high-performance libraries, game engines, or tight inner loops in C++ deliberately avoiding exceptions for error handling, even if the rest of the application uses them. They'll rely on error codes or return special values or maybe use newer techniques. Catching exceptions very close to where they are thrown can mitigate some of the unwinding cost, but the lookup and potential allocation overhead often remain significant bottlenecks on that error path.
Okay, so if exceptions can be that slow on the error path, how do the error values like in Go or with std.expected compare performance-wise?
This is where the value-based approach really shines from a pure performance perspective. Returning an error value like Go's result error pair, or using a type like C++23's std.expected-t, E, which is basically a discriminated union that holds either a successful value of type T or an error value of type E, has much, much lower overhead.
How much lower?
The cost is essentially just that of a standard function return plus a simple check, like the if err det nil or checking which state the expected is in. It's basically a simple branch instruction. Crucially, this low overhead applies even when an error occurs. The error path performance is very close to the success path performance. That Nutrient benchmark showed a dramatic performance improvement when they switched from using exceptions to an expected-like type for error handling in their test case.
So the performance reality seems like a huge contributing factor to why languages like Go went with the error value model from the start, and why modern C++ is actively exploring and adding these value-based approaches like std.expected alongside its traditional exceptions.
It absolutely is a key trade-off, yes. Exceptions offer that potential convenient and cleaner look for the happy path, but they come with potentially significant, somewhat unpredictable performance costs on the error path. Error values, while they can make the code more verbose with explicit checks, provide predictable low overhead performance for both success and failure paths.
It really highlights that error handling isn't some static, solved problem in language design. It keeps evolving, doesn't it? What are we seeing now, and what might be on the horizon based on the sources?
Yeah, absolutely. Languages are definitely iterated. We saw Java evolve over time. It added chained exceptions early on to help preserve the original cause of a failure when rethrowing. Then came try with resources for a much better resource cleanup. Multi-catch blocks were added to reduce boilerplate catch clauses. And alongside the rise of functional programming patterns, you see more use of types like optional to handle potentially missing values more explicitly rather than just risking a null pointer exception. And external libraries like Vav offer functional error handling types like try and either for Java.
Right, and C++ guys, always pushing boundaries, always debating.
C++ is definitely actively exploring ways to make error handling safer, more performant, and maybe less syntactically heavy in some ways. Discussions like those led by Herb Sutter, highlighted in some sources, point towards ideas like value-based or static exceptions. The goal there is to create an exception-like mechanism that performs much more like error codes on the actual error path, specifically by avoiding things like dynamic memory allocation and RTTI during the throw-catch sequence.
So, trying to get the best of both worlds.
Potentially, yeah, or at least offering more options. There's also ongoing debate about adding more explicit syntax, like maybe an explicit try keyword for propagation, to make the potential exception flow more visible in the code, addressing that common criticism that exceptions can be kind of invisible until they happen. And the discussion around better support for aggregate exceptions keeps coming up, potentially offering a cleaner way to manage multiple failures, maybe even addressing some aspects of that tricky destructor problem we talked about. These are mostly proposals, mind you, but they show the direction C++ is exploring, providing more tools, more control, and potentially lower overhead options.
Interesting. So C++ might be looking to incorporate some of the performance benefits typically associated with error values, while perhaps retaining some of the structured handling aspects of exceptions.
That seems to be a major theme, yes. Providing developers with explicit choices that have known predictable performance characteristics. Go, interestingly, has gone the other way for now. Despite all the ongoing developer conversations you see on platforms like Dev.to about the verbosity of if error, nil.
Yeah, people complain about it.
They do. But the Go core team has, for now, decided not to introduce new syntactic sugar or major changes to error handling. They seem to be focusing instead on improving standard library support for wrapping errors, adding context, and inspecting error chains, basically, making the existing explicit model work better, rather than changing the model itself. They're sticking to their guns on clarity and predictability.
Okay, so wrapping all this up then, we've really dug into this fundamental difference, haven't we? Between the implicit non-local jump model of exceptions, seen in Java and C++, say, and the explicit sequential checks of error values, championed by Go and increasingly available in C++ too.
And we've seen how that core choice deeply impacts not just the syntax you write, but the whole structure of the code, the safety guarantees you get, like with RAII, the maintainability, and maybe most dramatically, the performance characteristics of your software. Understanding the language's philosophy and the specific needs of your application is just paramount.
And why should you, our listener, really care about digging into these different approaches? Why does this matter day to day?
Because, fundamentally, every program you write or use or depend on will encounter errors. It's inevitable. How gracefully and reliably it handles those errors determines whether it's robust and trustworthy or brittle and frustrating. Being informed about these fundamental design choices helps you write better, more reliable code yourself. It helps you understand the trade-offs that the languages you use have already made for you. And it helps you debug problems more effectively when they, inevitably, arise.
So, thinking about everything we've discussed, that inherent tension between the potential performance cost of exceptions versus the verbosity of explicit checks, the safety nets provided by things like RAII and try with resources versus the complexities like that C++ destructor problem. Maybe the final thought for you is this. What kind of error handling design do you think best balances safety, readability, and performance for the specific kinds of applications you build or work on? It's a really core design question worth reflecting on.